Okay, so this is the first video in section 910, which is kind of the penultimate section in this chapter, not only because of its number, but because of its topic, and it's Taylor-Maclaurin series. This is really important stuff. So we'll probably spend at least a week on this. So let's see. So in the last couple sections that you've studied, you've learned what Taylor and Maclaurin approximators are and how they're used to fit functions, and you've also looked at how you can use power series to fit functions. But let's go back and remember that we began this part of the chapter, this unit, by just looking at what a power series was and its intervals of convergence, and remember checking the endpoints of the intervals. And we also learned that you could differentiate a power series term by term or integrate it term by term in order to do various things. And we looked at a couple different simple exercises in relation to those operations. In this section, we're going to learn that Taylor and Maclaurin series are a general way for differentiating power series and doing so for all derivative orders. So what the following theorem does is it says that every convergent power series, anytime a power series converges, you've got to not just differentiate it once or maybe the third derivative or anything, but you've got to do it for all derivatives. And what you're going to do is you're going to have the traditional power series that you use to represent a function, except you're going to be looking at where it converges, because if that power series does indeed converge down to the function, that's what we care about and will be the most useful. So you can see that this a sub n that we had before in power series is now going to take the form of the nth derivative expressed at the center of the interval of convergence divided by n factorial. Okay, we've seen where that n factorial comes in a bunch of times, so I'm not going to talk about it again. All right, so the main thing you want to pay attention to, I think, a lot is this definition here. It says if a function has all derivatives at the center of the interval of convergence that you're considering, then the series, this variation of the power series with an nth derivative in it, is called the Taylor series of the function centered in a certain spot. If you, of course, you pick that spot to be 0, then we call it the Maclaurin series. Those are just names, but I think that the names do have a little bit of impact on some problems, and they can be helpful if you think about the problems. Okay? So it says if you know the pattern for the coefficients of a function, you can extend the pattern to form the Taylor series. So let's look back at something we did in the last section, which was found like a fourth order approximator. So we did that for the natural log of x by just taking the various values of it. So I'm not going to go back and do that, but so this was the fourth order approximator for that. So if you want to form the Taylor series centered at that same spot, c equals 1, this is centered at 1, right? The approximator is centered at 1. Then all you have to do is basically extend that outwards. So instead of just actually computing a few of the coefficient derivative values, you have to instead find the like general form, and then you just keep going, right? And hopefully that Taylor series will actually converge down to the actual function. Okay, so let's look at one example where it says to do that with the sine of x. So we're going to look at a Maclaurin series. That means we must be centered at 0. All right, so let's see. So the first step in this is to just take a lot of derivatives and try to find an expression for the nth derivative of 0. So you take a lot of derivatives of sine. First you get cosine, then negative sine, then negative cosine, etc. We just did this in the last video, I believe. And then we're supposed to do it at 0 since we wanted a Maclaurin series. So now we're going to evaluate that. The sine of 0 is 0, right? Cosine of 0 is 1. Sine of 0 is 0 again. Cosine of 0 is 1, except now we're going to have a negative in front because of this negative, right? So anyway, you can see this is like a 4-step cycle, and then it repeats. So that's a little tricky, right? It's like got an alternating sign in it, but it's also 4 steps. So how could we come up with the nth derivative? So this is something I think that you probably haven't done yet. So the nth derivative evaluated at 0. So I think that we're going to want a couple things here, all right? So we want an alternating part, and you know what? Let's just do that, not just the nth derivative. Let's actually try to use the x of n value to help us. Okay? So we can see that every other term is going to 0, right? You have 0 to begin with, and then 0, and then 0. So I think that somehow we just want to pick like the even terms, don't we? We just want the even terms, and they're going to be alternating. So you could do that probably a couple different ways, but you can see that they've indexed starting at 0. So if we start with 0, the first term we want, the second term we want is, I should say the first term we want is going to be positive. So this is a little bit tricky. So let's just see what they've got. So they've got an alternating sign thing. That's no surprise, right? So the first thing when we put 0 in there is going to be positive. So we're going to go from positive. If we put 1 in there, it's going to be negative. If we put 2 in there, it's going to be positive. So you can see how that's going. Is that the way we want ours to be? I guess. I mean, if we exclude the 0 terms, we want positive right here. And then we want negative right here. And then we want positive right here. Make that a negative sign, I guess. So it looks like that is the way we want to go, right? So we want that -1 to the n term. If we're indexing at 0, it doesn't mean you have to index at 0, but if we go back to the definition, you can see that they've indexed at 0. You could probably shift your index if you need to, so don't worry if you have to shift your index or you find it starting at 1 to be more convenient. That's fine. Anyway, so we've got it going from positive to negative to positive, just like we want. So now how do we skip over the first term and the third term and the fifth term? How do we skip over those? Well, instead of just calling this x sub n, x to the n power, how about we use like an odd power thing in there? So how about we try like 2 to the n plus 1 to kind of say that we're going to skip. So now this depends on our index, right? If we put 0 in there, then we get x is attached to that first positive, right? So here over here, I might, off to the side, keep track a little bit. So our first thing is going to be positive. Let's see, how should I do this? So we're going to have a positive 1. And then the first value of x is going to be x to the, if we put a 0 in here, then we get x. So we've got a positive x. And I'm just going to put positive 1x to be a little clearer. So positive 1x. Then our next thing is going to be negative, right? So we're going to have -1, and if we put 1 in here, then we get x to the third. And then the next thing is going to be positive 1, and then if we put 2 in there, we get x to the fifth. And then we'll do one more, so it would be negative, right? So, if you're confused about this, go back and look at, so 0, 1, 2, 3. If we put 3 in, then -1 cubed is of course negative. And if we put 3 in here, then we get x to the 7th. So you can see how this is skipping over, and it's because of this 2n plus 1 guy. You could go 2n plus 1, you could go 2n minus 1. I don't think it really matters except that it fits the actual series of derivatives that you've come up with here. So that's what you really have to be careful about. So that's what's left. So all those other terms are going to go away. So you can see that you've got your 1x, your -1x cubed, your 1x to the fifth, and your -1x to the seventh. And then now let's look at the bottom part. So when you do these, we skipped some, right? So we don't want to just say n factorial, because if we put just an n factorial down there, then we'd have like this guy. But remember, n for this guy was 1, so it would be like over 1 factorial. That's not the way that's supposed to work. Then this would be like over 2 factorial. That's not the way we would want that, right? This is supposed to be over 5 factorial. So you want that 2n plus 1 thing also on the bottom. That way you get that the exponent matches the factorial term, okay? And then it says by the ratio test you can conclude that this series is convergent for all x, so I guess we'd have to apply the ratio test. We're not going to do that on this one. Okay, I hope you found this useful.